بسم الله الرحمن الرحيم اقرأ باسم ربك الذي خلق خلق الإنسان من علق اقرأ وربك الأكرم الذي علم بالقلم علم الإنسان ما لم يعلم كلا إن الإنسان ليطغى أن رآه استغنى إن إلى ربك الرجعى أرأيت الذي ينهى عبدا إذا صلى أرأيت إن كان على الهدى أو أمر بالتقوى أرأيت إن كذب وتولى ألم يعلم بأن الله يرى كلا لئن لم ينته لنسفعا بالناصية ناصية كاذبة خاطئة فليدع ناديه سندع الزبانية كلا لا تطعه واسجد واقترب
Bismillahirrahmanirrahim. Ladies and gentlemen, we are starting our second day of the second international conference on polymers and composites. And today our first keynote speaker is Professor Dr. Azam Hassan. He is from University Technology, Malaysia. And he is currently a professor in Faculty of Engineering and Center of Advanced Composite Materials at UTM. He obtained his PhD in 1997 from the University of Loughborough in polymer technology. He was the head of Polymer Engineering Department, Deputy Director of Research Management Center, and he held other key administrative positions. He has supervised more than 30 PhD students and published more than 250 research articles with the Scopus H index of 32. In 2016, he was awarded with the Top Research Scientist Malaysia Award by Academic Science Malaysia. So over to you, Professor. His topic is on polylactic acid, which is a versatile bio-based polymer for the future. Over to you, Professor.
Okay. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. Can you see my slide?
Yes, Professor. We can see your slide. Kindly continue.
Okay, you can hear me as well. Okay, thank you to the session chairman, Dr. Zubair Khalik, and also to the co-chair, Dr. Faiza Anjum, for chairing the session this morning. And I also would like to thank the organizing committee of the Second International Conference on Polymers and Composites for inviting me to deliver this keynote lecture. Okay, the topic for my presentation this morning is polylactic acid, a versatile bio-based polymer for the future. Sorry, the slide is not moving. Okay, it's okay now. All right. Firstly, I would like to introduce from where I am from. Where is University Technology Malaysia? So you can see the map of Malaysia there. We have the Peninsular Malaysia and also the East Malaysia. So University Technology Malaysia is located in two places, one in the capital, Kuala Lumpur, and the other one is in Johor Bahru near Singapore. So the main campus is in Johor Bahru, and we have another city campus in Kuala Lumpur. So the top picture is in Kuala Lumpur and the bottom one is the campus in Johor Bahru. The content, these are the topics that that I will be presenting this morning. I have divided into 6 subtopics, and I hope that I will be able to cover that within the 30 minutes allocated for me. The first one that I will be talking is about a little bit general introduction about polymers, contribution, and problem. Okay. I would like to start with a story from a film that was being produced in 1960 about a discussion between an old man by the name of Mr. McGill and a young man who has just graduated by the name of Benjamin. The title of the film is The Graduate. So when Mr. McGill met Benjamin, he said, I want to say one word to you, just one word, plastics. And then Benjamin asked him, exactly how do you mean? Mr. McGill said, there's a great future in plastics. So that was the incident which happened around that time in 1960s. And actually, that is true. There's a great future in plastics. Plastics, the miracle synthetic polymer material, became very popular in 1960s. Plastics was everywhere, and the application is vast application for plastics, and there seemed to be no end to which plastic could be used. What are the benefits of plastics products? Plastics are lightweight and durable and versatile in color, touch, and shape, which gives tremendous marketing advantages compared to other materials. And the properties of plastics can be modified through the incorporation of additives. There are various additives which can be incorporated or can be added into polymer, and also by blending with other polymers to enhance and to improve the properties of plastics. And on top of that, the production of most plastic product is not energy intensive compared to metals, glass, and paper. If we look in the transportation industry, we can see that the use of plastics can bring about a significant saving of fuel and lowering of operating costs. As example of the 22% of an Airbus A380 double-decker aircraft is built with lightweight carbon fiber reinforced plastics, giving such advantage. And in the packaging industry, without plastics, packaging weight increase by as much as 400%, and production and energy costs could double. And now let us see what is the current reality in the year 2022. Plastic is one of the most successful material ever produced. So much so that 300 million tons are being produced each year. With that, said to say, plastic poses severe environmental problems because not biodegradable and hang around in environment for decades or even much longer. In 2018, a Pacific Ocean garbage patch was estimated to be 2 times the size of France. Okay. And in ocean, another problem is that the plastics break down to microplastics, which is very small in size, which can be taken up by marine life. And if things do not change by 2050, it is expected that there will be more plastic waste in the ocean than fish. And now plastics problem is everyone's problem, as mentioned by the Vice President of European Commission. Single-use plastics that take 5 seconds to produce are used for 5 minutes, then take 500 years to break down again. So that is the reality that plastics is giving the problem to human being. What are the ways that have been thought to solve the plastic pollution problem? Number one is reduce the amount, and then to reuse the plastics, not only using once, and we can recycle to other products, and to educate the masses on this problem. And let's see what are the true facts about plastic waste recycling. Currently, more than 300 million tons of new plastic is produced annually, and less than 10%, only less than 10% of it recycled. Mass production of plastics, which began 6 decades ago, has accelerated to creating 8.3 billion metric tons, and 6.3 billion metric tons has become plastic waste. And it was noted that most single-use plastic, like those shopping bags, never gets recycled. Then what should the government do? Okay, it is not an easy task, because banning consumer plastics harms both consumers and environment. Plastics have certain advantages. Plastics is safer to use, since reusable bags often harbor bacteria and could pose another problem, health problem to the consumers. And plastics has the advantages of use less energy because of the lightweight during production and transport. And plastics are economical, it is cheaper than other materials. Okay. Now, I'm going to the second part of my presentation on the PLA synthesis properties and application. Okay. I would like to explain the term biopolymers, because it is a term which is sometimes misunderstood. Polymers can be divided, either it is bio-based or it is fossil-based. And the bio-based, if you look on the upper side, it can be non-biodegradable. It is bio-based, but it is non-biodegradable. For example, bio-based polyethylene, PE, PA, and PTT, which are being recently being produced. It is bio-based but not biodegradable. And there are polymers, there are another category of biopolymers which are both biodegradable and bio-based. For example, polylactic acid, which we are talking this morning. And then we have fossil-based but biodegradable. For example, PBAT or polycaprolactone. And the conventional plastics, which are both non-biodegradable and it is not bio-based. For example, the most popular one, PE, PP, PET, PVC, and many others. So, in short, we can say that in order to be characterized as biopolymers, it must be either it is bio-based or biodegradable. It does not need to be both. But there are few exceptions where certain biopolymers are both biodegradable and bio-based. What is polylactic acid derived from? Okay, lactic acid are produced from fermentation of sugar, and then from this lactic acid, it is polymerized into polylactic acid, and later on, after being used, it can break down into carbon dioxide, water, and biomass. So you can see the cycle of the polylactic acid. Another question is polylactic acid the solution to the pollution problem? The answer is not easy. It is complicated. Manufacturers and environmental experts who warn of the potential merits of polylactic acid rest on many ifs. Okay, the marketers of polylactic acid like to stress that PLA is a biodegradable polymer in total. Okay, it is true that it is biodegradable, but only at some point. The biodegradation process actually will take several hundred years in a typical landfill. So, in order to biodegrade, PLA requires a list of conditions to effectively break down. It needs oxygen, temperature of around 140 degrees Fahrenheit, and organic substrate. And these conditions are available in the industrial composting facilities. Therefore, PLA is actually not biodegradable, but it is a compostable polymer. Beneficial properties of PLA. Firstly, as I have mentioned, it is eco-friendly. It is derived from renewable resources and compostable. It is biocompatibility. Therefore, it is suitable for biomedical application. PLA degradation products are non-toxic, so it is suitable to be used for biomedical application. The degradation products do not interfere with tissue healing. Thirdly, PLA has better thermal processability compared to other polymers such as PHA and PSL. So this is a great advantage for PLA. And it energy savings compared to other petroleum-based polymer requires 20 to 50% less energy. And in terms of properties, it has good mechanical strength compared to many polymers, and also being polymer, the properties can easily modify to improve. For example, to improve the flame retardancy, to improve the brittleness, and so on. What are the limitations of PLA? One is the degradation rate is very slow. It takes a long time, but it can be made faster when we have simple machine to do it. PLA is very brittle. It is very brittle and less than 10% of elongation at break. It has limited gas barrier properties, which prevents its complete access to industrial sectors such as packaging. It has higher costs compared to commodity plastics such as polyethylene or polypropylene. It has low melt strength, low crystallization rate. So the percentage of crystalline is rather low, poor processability, and low service temperature. compared to other polymers. So we can see here comparison between PLA and acrylonitrile butadiene. We can see that the tensile strength is much better for PLA. The modulus of elasticity or the fractural modulus is very good, but it is inferior, especially in elongation and break and impact strength. That's why PLA is considered to be relatively brittle. The routes for PLA synthesis from lactic acid, there are three routes to produce polylactic acid from the lactic acid. And the most popular one is the two steps polymerization. The other one is the direct consolidation of the lactic acid and also the ring opening polymerization of lactates. Okay, the new development in the synthesis of polylactic acid is the application of agro waste to be the source for the production of lactic acid, which later on to be polymerized into polylactic acid. So me and my co-workers has written an article in a book titled Bioplastics from Agricultural Waste. And in that book, we have stated that renewable agro waste such as bagasse, wood waste, empty fruit bunch, starch material, and chitosan have been used for bioplastics production, namely for PLA. So what are the applications of PLA? Mainly, it is used in agricultural for films, consumer goods, various consumer goods, medical, especially in scaffold and skin tissue repair, and also for food packaging. Okay. Thirdly, now we are going into types of PLA modification. The two main types to improve the competitiveness, to improve the properties of PLA is, number one is by blending with other polymers, and number two is the incorporation of additives. Polymer blending. So in general, polymer blending is an effective, simple and versatile method compared to synthesizing new material or co-polymerization, and we can develop new materials with tailored properties. So we can know what properties exactly we want to achieve by blending the right polymers at the right proportion. One of the most basic questions in blends is whether the two polymers are miscible or exist as single phase. But most of the time, blending two polymers will not result in miscible polymers. They are mostly immiscible polymers, but we can improve it by making it more compatible. So in many cases, the polymers will exist as two separate phases. So the morphology of the phases is of importance. We need to know which one will form the domain and which one will form the particle, and how big is the particle size. In order to improve the compatibility between two polymer blends, the role of compatibilizer, which is another chemical, is very important. So this study on the role of compatibilizer is very actively being done by many researchers. I would like to share one review article on the polylactic acid blends, processing properties and application, published in International Journal of Biomicromolecule, written by researchers from Turkey, from Istanbul Technical University, where they said that there are various types of PLA-based blend. PLA, the most popular one is PLA binary blends with other polymers, with other biopolymers, which can be blends with only biodegradable polymers, or only bio-based polymers, or blend with polymers which have both properties, bio-based and biodegradable, which I have mentioned just now. And also PLA binary blends with synthetic non-degradable thermoplastics like polyethylene or polypropylene, and PLA blends with elastomeric polymers, which rubber, for example, natural rubber and so on. And on top of binary blends, which have two components, there also have been reports on ternary blend, and also we can see there are also PLA blend which have fillers or reinforcement, which we call, if the fillers is in nano size, we can consider it to be PLA blend nanocomposite. So in terms of popularity, we can see that polymers which are very popular, there have been many reports which have been blended with PLA are PCl, polycaprolactone, starch, PHA, and PBAT. The reason because blending with such polymers will produce final products with full bio feature, because they themselves are biopolymers. What are the types of additives that have been used to modify PLA? Firstly, fillers. Fillers, depending on the size and structure, it can be considered to be micro fillers, nano fillers, which the fillers have one of the size less than 100 nanometers, or it can be considered fibers if it has a good length to diameter ratio. And impact modifiers, namely rubbers and flame retardants, are also popular additives which have been used to improve polylactic acid. So for the nanofillers, many reports have been available in the journals on the use of monomerilonite, halosite, graphene, and carbon nanotube. And the performance, the properties which improve with the addition of these nanofillers are namely mechanical, especially the modulus and strength, flammability, thermal barrier, and antimicrobial. Okay, we're going on the fourth now, on the 3D printing of polylactic acid. There are namely 5 ways of PLA fabrication: 3D printing, casting, injection molding, which is very popular, extrusion, machining, and solvent welding. And lately, 3D printing is becoming very popular, and many research has been done on the 3D printing, including the 3D printing of PLA. So for those who are new to 3D printing is the construction of a 3-dimensional object from computer-aided design model with material being added together, typically layer by layer. What are the advantages of PLA as 3D printing materials? Firstly, it is of the low printing temperature, relatively low printing temperature compared to other thermoplastics, because of it is low TG and also low crystallinity. Therefore, it less likely to warp and clog the nozzle during the printing press and produce better surface details and sharper features. It is easy to use, and it can be modified with various additives, as I have mentioned, easy post-processing, and it is an eco-friendly material. So, based on this paper published in Progress in Polymer Science, the majority of polymer materials currently used can be divided into 2 classes. Either it is thermoplastics without any reinforcement, or thermoplastics composites. And polymer thermoset and elastomic elastomer materials for 3D printing are just only recently emerging, and there are not many reports being published on polymer thermoset and elastomer materials for 3D printing. So this review paper provides an overview of the recent advances, especially on thermoplastic and composite materials. And also there are many suggestions on the need to improve their performance and properties. So this will be interesting for future research, especially on the various additives in PLA for 3D printing. The review paper reports various studies for particle reinforced composites by the use of hydroxyapatite, natural fiber reinforced. There is a paper on jute fiber, synthetic fiber, carbon fiber has been used, and also nanomaterial reinforced composites by the use of polyurethane and also graphene oxide. These are some of the papers that was published based on PLA for the use in 3D printing. Now I would like to share on some of the past and recent research on PLA modification. I have published more than 20 papers on PLA blends, composite, and nanocomposites being published in various journals. You can see in the slide. Starting, the first paper is the one on the right, top right, published in 2010 in the Journal of Elastomers and Plastics with my master student at the time.
Professor, we are a bit behind the schedule. Kindly complete.
Okay. All right. So in this paper, we have used 5% of carbon nanotube, and we vary the rubber content. And we can see that the impact strength, the CNT reduced the impact strength of PLA, but the natural rubber was effective in enhancing the impact strength of both PLA and PLA CNT. So we can see that our own natural rubber, which is being produced in our country, is effective as impact modifier for PLA. And we have come up with the most optimum formulation by the use of natural rubber at 10%, which give balanced properties in terms of tensile strength and elongation and break. So these are the main findings. And the second paper, which is very recently, is the use of polymethyl methacrylate to improve the compatibilization of PLA and with ABS and SAN. And it is very interesting. We can see that the PLA has improved and it has been supported from the contact angle measurement. We can see here the PLA has low degrees of contact angle compared to SAN and PLA, resulting in improvement of impact strength at addition of 4 weight PMMA content. Okay, and it also has been seen that for the 3D printed structures, it is comparable. It is much better than polystyrene only. So the study have shown very good results for the use of PLA in 3D printed structure. And the other one is the use of, the last one, the use of low loading of ammonium polyphosphate. And it has been shown by the simultaneous use of resorcinol, bis-diphenyl phosphate, and APP. We have produced, they have produced a good flame retardant PLA composite that can also be used for 3D printing. It has good mechanical properties and also it has good flame retardancy. Okay, so these are the main findings. The formulation is the use of 2% of APP and 0.12% of RDP. Okay. The last one I would like to touch is on the challenges and future direction. So the challenges is to reduce the price of PLA and also to address the biotechnological production by improving using high performance lactic acid producing microorganisms, lowering the cost of raw material and lowering the cost of fermentation process. And also to further study on the use of catalyst, which has low toxicity so that it can be used for biomedical application. And there are vast opportunities to improve PLA based on blends and fillers that will expand the domain of application. And also there are need for further research on the use of PLA blends, PLA composite, and PLA based blends composite for 3D printing. With that, thank you for your attention. And if you need further or you want to contact me, I have written my email here at UTM. Thank you very much. Okay.
Thank you, Professor. It was indeed a very informative presentation regarding polylactic acid. We are facing serious problem of plastic waste nowadays. I'm again thankful for your keynote speak. Thank you. And for our next keynote talk, I would like to invite Professor Gillis Lubino from King Abdullah University of Science and Technology. And Professor Gillis is affiliated with Mechanical Engineering Department, and he completed his PhD in Mechanical Engineering in 2002. And his research interests are computational modeling and experimental development to tackle complex problems related to composite engineering. So over to you, Professor Gillis.
Hello, good morning. How are you doing? Can you hear me? Or?
Yes, Professor, we can hear you loud and clear. Kindly continue.
Okay, perfect. Thank you. So, good morning, everyone. It's a pleasure to be here to give you a presentation about our research this morning. I wanted to thank the organizer for inviting me this morning and for this beautiful program that they assembled during these 2 days. So, from my side, what I will discuss with you this morning is more about how you are using composites in bonding and the way you can design interface. Can you see my pointer here, my mouse moving? Yeah. No?
Yes, Professor, we can see your pointer easily. Yes.
Yeah, good, perfect. Okay, so here I will discuss more about interface and delaminations and how you can control the morphology of interface to control the delamination. So the work that I will present today, it has been done. I don't know why it doesn't want to move now. Sorry. Sorry, why it doesn't move. Okay, it has been done with together with my collaborators. So Arifu Danto, Rantao, Ahmed Wagik, Shaoleli, and Majid Hashem in a place that is called the Laboratory of Mechanics of Composites for Energy and Mobility. And this was part of the Office of Sponsored Research Programs. It was a funded programs by the Central Chaos Administration. So why bonding? So bonding is something that is extremely important in many different industries. So for example, if you go to aeronautics, or if you go to civil engineering, or if you go to renewable energy, wind energy, for example, or if you go to automotive engineering, there is a lot of situations where you want to assemble together metal to composites or composites to composites. And this becomes increasingly important when you are moving towards complex structures. And the way this is done today, with what you call conventional fastening technologies, this is done by using a lot of rivets and bolts. So that means you introduce drilling, you introduce stress concentrations, weight. This results in a weight increase. From an economical point of view, this drilling requires a lot of labor, and if you go to the life cycle, same thing in terms of maintenance and repair, it's complicated. So what people would like to do when it comes to bonding, they would like to go to what you call integral adhesive bonding. So that means you just have two pieces, a part one, a part two, and then you put an adhesive in the middle to make sure that you can connect them without any mechanical interlock. So this is attractive, but the confidence is limited. That means it's difficult to measure and to inspect the initial response, the initial strength of such adhesive. Usually these ones are going to behave in a brittle way. The performance is very sensitive to the adherent surface preparation. Means the way you prepare your substrate when you are doing the bonding. And this usually is made by using different type of mechanical treatment. Operators, but this is going to introduce dissimilarities across treated interface, or chemical treatment, but this will result in a lot of chemical waste, but will also introduce health and safety concern. So what we want to do here is to improve the confidence in this bonding. So there are different strategies to do this. The first strategy is to introduce what you call corrugation of the substrate and mode mixity. So how do you introduce connection or bonding between the substrate without mechanical interlock? So here people are going to shape the substrate. So for example, they are going to make embossing, or they are going to make corrugation, and this corrugation and this embossing are going to make the delamination more complicated. Other strategies are based on introducing real interlock between the substrate. So here, for example, you have a composite substrate, a CFRP substrate, another CFRP substrate, and then you introduce a morphology of the interface that is going to, here again, to fight the delamination. This is efficient, but this results, of course, in a very strong modification of the substrate and of the global performance of the system. I don't know what to do with this zoom bar every time. Okay, then something that you know very well in composite engineering is what you call the Z pinning. So that means you are going to come with pins that you will introduce within the substrate by using an ultrasonic gun. So this is something that will result like this into out-of-plane reinforcement. But here again, this is going to damage a lot the substrate, because you know that this introduces a lot of perturbation of fibers, and there are real questions about the integrity of the substrate. Then you have some people who also modify the interface. What I mean is that if you go to all these techniques, what is important to understand is that they all modify a lot the substrate, and they all modify a lot the quality of the substrate. So what we want to do here is to introduce a new technology to reinforce the interface that is based on a single strategy that is about promoting long-range bridging. That means when you have delaminations, we are going to try to reinforce the interface by introducing these fibers that are going to bridge from one substrate to the other one and introduce what you call non-local toughening. So this is something that is important for us, because what we want to do, we want, in fact, to improve three things. The first thing is that we want to improve the intrinsic performance of the adhesive joint. So that means we want to make sure that the joint by itself is going to be tougher. We want to change the failure of the joint from being brittle to a progressive failure by design. That means we don't want to have unstable delamination. We want to stabilize this. Then we want to do this without compromising the substrate. So that means everything that we are going to do as strategies, everything is going to be done in a way that we are not going to modify the substrate, we are not going to compromise the substrate. So for this, I will present to you today 2 to 3 different strategies, depending on the time. So the first one is, how do you promote toughening and long-range bridging by introducing what you call structuration of the adhesive substrate interface? That means you have the adhesive, you have the substrate, and how do you modify the morphology of the interface to make sure that you will modify the response of the interface? Then the second strategy that will be by introducing an hybrid adhesive. So if I look at the adhesive here, we are going to make hybrid adhesive that will be either modified by using an additive approach, so that will be a blend of thermoset and thermoplastic, or by using a subtractive approach. That means just by introducing what we call sacrificial cracks. So that means pre-designed defect in the adhesive, how this is going to modify the response of the joint. So if I go to the first technology, the one that is about this one, that is changing the structuration of the adhesive substrate interface. So this will be what I call path one, that means structuring the adhesive substrate interface. So how do we do this? So the first thing that you need to do here is to have a tool to modify the surface of the surface at the interface between the adhesive and the substrate. So usually we do this by using laser treatment. So I guess everybody here is very used to laser treatment. So what you use, that you are taking a laser beam, and then this laser beam is going to introduce a high density of energy on the surface, and depending on the wavelength, you can get different type of results. So here we are using, for all demonstration, we are using a CO2 based laser with a 10.6 micron wavelength. So here, what is important to understand in laser treatment is that depending on the what you call the fluence, that means the density of energy that you introduce on the surface, you can go from at low fluence. So for example, here 1.2 joule per square meter, you can get relatively low modification of the surface. So this is going to be only modification of the local morphology. I mean, cleaning the surface, or you can completely evaporate the resin, and you can expose the fibers, so you can get strong modification of the morphology when you go to high fluence. For example, here 3 joule per centimeter square. So this surface treatment, they influence a lot the surface properties of the composite, because if you go on a weighting plane, for example, if you look at the polar and dispersive component of a weighting test, here you have the weighting envelope that you have on a pure Teflon surface. I mean, on a CFRP treated with a Teflon film, and here the weighting surface after laser treatment. So you see that the first effect of the laser treatment is to improve the weighting, and this is due to the introduction of polar groups on the surface. If you look at the number of polar groups, that means functional groups that are going to be polar on the surface, these are increasing with the laser treatment. So this is the first effect. The second effect of the laser treatment is really a cleaning effect, because if you look at the gray bars here, this is related to the silicone content on the surface that comes of the fabric that you are using during the processing of composite. And you see clearly that the first effect is to clean the silicone. And you know that the quantity of silicone is very related to the toughness of your interface. So when you start to have silicone on the interface, you pollute the surface, and this is detrimental to the quality. So this surface treatment has two main effects: removing any kind of contamination like the silicone, or introducing some functionalization that will help the bonding. So what we do is that we are going to use this laser treatment, and this laser treatment is going to be used with different level of energy to introduce some pattern, some variation in space of the interface property. But before we go to the experiment, what I want to show you is that how can we control the fiber bridging, or let's say the ligament formation, or the response of this interface by introducing heterogeneities on the interface. And this we do it with a numerical study, that will show you what is the effect of search patterning. So imagine that, so first I will start with a simple numerical simulation. So imagine that I'm taking a DCB sample like this. So a DCB sample in which I have the two substrates. So these are the two gray are the two composite substrates. In the middle, I have an adhesive layer, that is an epoxy layer here, that is a yellow layer. And then between the epoxy layer and the substrate, we are putting an interface, but this interface, we will assume that this one is non-uniform. Instead of having uniform interfacial properties, we will assume that there are some tough regions that are, for example, the dark gray here. So here, if I look at the sigma at the opening separation curve, the traction separation curve, so sigma delta, the stiffness is bigger and the toughness is bigger. If I go on the light gray here, on the light gray, I introduce some surfaces that are weaker. So this experimentally, this is easy to do by using different level of energy by using the laser treatment. And then what I would like to see is what's going to happen in terms of delamination if I start to play with the contrast of properties between the dark green and the light green. So here, the first situation that can happen is that this is not going to modify anything. That means the contrast is not very big, and then you would get a classical, if I look at the classical delamination curve, the opening is going to be the same as usual. The quark is going to propagate at the interface, and when the quark is reaching the tough region, by just locally the toughness is bigger because you have a tough region, but you are not going to change any type of mechanisms, and then the delamination is going to continue. So this is the first situation. Just a quark is going to propagate at the interface here between the adhesive and the substrate. And this quark is going to go through different regions with different surface properties, with different fracture properties, but without modification of the mechanism. The second thing that might happen is that now, when the quark is propagating at the interface on the bottom, when this quark is going to hit the tough region here, this region is so tough but the delamination is stopped here, and you introduce a bifurcation of delamination. That means the delamination will start on the top here. And then what's going to happen is that, in fact, you are going to create a ligament like this. So what you call a bridging ligament, that is going to bridge the top substrate to the bottom substrate. And in this case, this, of course, is going to modify a lot the delamination curve, because at the beginning, you follow here the classical delamination curve when you delaminate on the bottom. But as soon as you create this ligament, you are going to store a lot of elastic energy, and you are going to stabilize your delamination curve. So the load is going to be much bigger compared to the original separation. So this is something when you look at the simulation, that means that you get something like this. That means when the quark is coming here on the bottom, there will be a bifurcation, and you are going to create a bridging ligament here with, in fact, 3 quarks that are propagating at the same time. 2 quarks, sorry, one on the bottom here and one on the top between the ligament and the top substrate. The third situation that can happen is the situation where you do exactly this. That means the quarks start to propagate on the bottom. It reach the tough reinforcement, and you start to create this ligament, but the bottom is so tough that at the end, you cannot really propagate both quarks. You are going to break the ligament. So this is what you see here. You have ligament breakage. So that means that you need to optimize the contrast between the light green and the dark green, because if you are not tough enough, you are not going to get this bridging. So if this is not strong enough, you are going to get the classical delamination. But if this is too strong, you are going to break the ligament. So you are going to limit the performance of your reinforcement. So what you can do when you understand this is that you can start to optimize your surface treatment, and you can look at what is the optimal strength ratio and the optimal toughness ratio between the dark green and the light green. So you optimize this mechanism. So you promote the mechanism with ligaments, the one that is here, and you make sure that you always get this one. And then you can see that there is a design space here in which you need to optimize your contrast between 1 to 1.4 in strength and 1 to 1.5 in toughness. So you really create these ligaments. And then you can see if you can do this experimentally. So this is really what is interesting to us. Now that you understood the concept from a numerical point of view, but you can introduce some experiment. And this is what you can see here. So what we do is that we are taking 2 composite plates, and on each composite plates, we introduce this kind of local laser treatment. So that means you have 2 treatments here. You have a dark green that is here, that is going to introduce high toughness, high strength. And then in between, you just have a surface cleaning. And this, when you start to make delamination on sample like this is the mechanism that you observe. So you observe exactly what you want to see. Instead of having a very neat interfacial quark at the middle here that is not going to dissipate a lot of energy, here you start to introduce a lot of fragmentation of your interface with a lot of bridging ligament. If I make a pause on this, you are going to introduce a lot of bridging ligaments here that will bridge the top substrate to the bottom substrate. What you see here is that you can see here, if you look on the right of the screen here, what you see is a fractography on the interface. And you see here again that you have a lot of dissipation on the interface with a lot of bridging event and a lot of subsquarks and so on. And this you see this on the delamination curve. If I look at the delamination curve here, but you see very clearly that the P delta curve is much higher compared to the initial DCB curve with a lot of secondary events. So you see a lot of quark jumping events here that are all related to the formation and breakage of different ligaments, 1, 2, 3, 4, 5. And if I look at the apparent toughness of the system, so this is very important. The apparent toughness of the system is going to increase by 300% because you will jump from 0.3 kilojoule per meter square to more than 1 kilojoule per meter square. So you have a huge improvement of the performance of your joint when you do this, and your joints becomes much more stable. Okay. So this is something that I presented here in mode 1. You can do exactly the same kind of studies in mode 2. In mode 2, of course, the kinematic of the joint is different, so the reinforcement is different, but you see the same type of effect. If I look at the P delta curve for baseline treatment, the black curve here, or if I look at the blue curve here, when you reinforce with a pattern of quarks, like with a modified surface treatment, you are going to improve the response in mode 2. So what I would like to show you now is how you can use this for real applications. So here, for example, you have a T-joint. You know that T-joint, it's a very classical structure when you go to stiffeners and things like this, when you want to glue stiffeners to composite panel. This is something that is really interesting in terms of structures. And this is the kind of degradation that we get when we are using our surface treatment. So what we do here is that instead of gluing directly the T-joint to the composite substrate, we modify the composite substrate with some surface treatment. And you see that by doing this during the delamination, you introduce a lot of bridging events here that are going to reinforce your T-joint. And what is the consequence of this? But this is, if I look at the load extension curve, that means the force as a function of the displacement when I pull on this T-joint, but this is the original curve, the black one. And this is exactly the one that what you get when you start to modify the surface, the composite surface by using this laser surface treatment. And you see that you have a huge improvement in the ductility of the T-joint when you go more than 20 millimeters. So, so this is the first strategy that I wanted to present to you. That means a strategy that is based on modifying the composite substrate by just introducing heterogeneity by using patterns laser treatment. I will present to you now just a second technology that is based on structuring the adhesive by an additive approach. So this will just take 2 minutes. Another technology that we are using in the lab is to modify now the interface by using hybrid thermoset and thermoplastic. So the idea is that if you reinforce, the idea is again to introduce bridging between the top and the bottom substrate, but this bridging is introduced by a thermoplastic net. That means that the thermoplastic net, you know that thermoplastic have much more ductility compared to thermoset. And if you are able to achieve bridging by a thermoplastic net between the top and the bottom substrate, you will also stabilize a lot your joint. So the way we do this is that in fact, we introduce within the adhesive layer, we introduce a 3D printed thermoplastic net that is going to be inside the epoxy layer. And then what is important, if you are able to control correctly the processing and the morphology of this film, this is a kind of delamination that you are going to get. That means here when you start to delaminate this composite, instead of having a classical quark, here you have a quark with a lot of stretching of thermoplastic filament, and these thermoplastic filaments are going to dissipate a lot of energy. So this, I will not go on the detail on this, but this is very related to the level of porosity that you are able to control between the thermoplastic and the thermoset, because if you don't introduce, if you try to make a good joint, that means if you don't introduce enough porosity, what you will see is that the improvement is very limited compared to the initial configuration. That means if you go to the dark blue curve, that is what the delamination curve that you get in case of delamination without porosities, but you get a relatively limited improvement compared to the control sample in black here. But as soon as you control the morphology of your porosity, you see that the improvement is huge compared to the control sample. And why? But mainly because if you introduce porosities, you give a lot of freedom to the thermoplastic to deform and to stretch during the delamination. And this is what is important. Okay, so I will try to bring you, I mean, to save some time to make sure that we stay on schedule. So this one I will present another time, but is about another approach, and I will go directly to the conclusion. So in terms of conclusion, what I wanted to present you here are different approaches that you can use to manipulate the failure during secondary bonding of composites. That means when you take composite to composite and you make an interfacial bonding. We do this either by introducing heterogeneities on the adhesive substrate interface, or by introducing additive heterogeneities in the interface. So this is the last thing I have shown to you in terms of thermoplastic hybrid. Sometimes these heterogeneities that can be, instead of thermoplastic, they can be sacrificial cracks. So this is a third approach that I did not present today. But what is important is that all of these, they are all compatible with what we call an all-in-adhesive concept. That means that we don't touch at all to the substrate. We just come with an adhesive film, and this adhesive film is encapsulated in between two substrates. So that means there is no modification of the performance of the substrate. So what we do now is that we try to go towards an integration of a highly engineered adhesive system. So that means an adhesive system in which we put all these ideas together between the thermoplastic film and a patterning on the surface, and try to encapsulate all together to make sure that we get an adhesive that you can take as an engineer to put between your composite part and get super high toughness. So there are a couple of related publications on this. So publications on either on the modification of the interface, or modification of the substrate by laser treatment or bioinspiration. So you are very welcome to have a look at these different papers, or to send me an email if you cannot find some of them. I will be happy to share them with you. And I wanted to thank you for your attention. Here you have my email if you need more information, and then you have the website for the lab if you want to see what we are doing now. Thank you very much for your attention.
Thank you, Professor, for the very informative talk. It was indeed a very unique idea of the substrate or adhesive texturing by imparting some heterogeneous systems on morphology. We have a few questions here from our from Dr. Yavaskar. He asked that, can we use sandblasting technique to modify the surface for bonding?
Yeah, so sandblasting, it's a very good technique, except you need to be careful to a couple of things. First, you need to make sure of the cleaning that you are doing afterwards. You need to make sure of the level of energy to make sure that you are not going to damage your fibers. That can happen sometime when you do sandblasting. And you need to be careful if you want to use it. The point here is to make a surface treatment that is non-uniform. So that means you want to be able in some area to have some arch surface treatment, and in other area to have no surface treatment. So if you are able to do this with sandblasting, but you can do if you put mask or things like this, there is no problem. You can use sandblasting. It's a good technique to do this. Yeah.
Okay, this is the continuation of the question, that how to avoid the void formation during bonding, as voids become starting point for cracking bonded substrate.
So this is interesting because if you look at void, sorry, can you still see my screen or not?
Yes, we can see that.
Voids are not always, you don't want always to avoid voids. For example, if you go to this technology here, this is exactly what I was explaining. You have here on the left, you have two configurations. On the left, you have one configuration with few voids. I mean, you have voids, but compared to the one in which you have big voids on the right. And sometimes, for example, in this technology, you want to have porosities. You want to have voids because voids are a way to introduce a porous structure that is going to dissipate a lot of energy. Then, really, if you want to introduce voids, that is what you do in classical composites. The only way that you can introduce them is first to be very careful when you make your co-bonding to make sure that you don't trap air inside, and then you go with the classical vacuum plus pressure systems to make sure that you can suck your hair, right? That's yeah.
Okay, Professor, we have the last question from Professor Tahisha. He asked, can you comment on sacrificial cracks and their role in ADM?
The sacrificial quarks, it's a different idea. It's when you do something like this, for example, that means here what we do is not very clear on the picture, but if here you have two substrates, and then on the middle there is an adhesive layer, and here you introduce a sacrificial quark. That means that there is a Teflon film from the beginning here that you can see in blue here. And we introduce Teflon film that are going to be quarks from the beginning. And this one, it's important because when you do this, the same thing, the role of this interfacial quarks is to make sure that we introduce quark bifurcations and we modify the failure mechanism. So you see here, typically, instead of having a single quark delamination, due to the sacrificial quark that is here, we are going to introduce a bifurcation in the ligament. So it does not modify the adhesion per se, but what it does is that it modifies the redistribution of stresses and the stress concentration and everything. So it will promote different mechanisms, and here typically it promotes bridging and dissipation. Yeah. So
Thank you, Professor. I hope, and we are very thankful for your time and your keynote speech. It was really informative, and most of our panelists got their answers. Thank you.
Thank you very much. Thank you.
Thank you. For our next presentation, it will be presented by Dr. Asif Jamal from University of Engineering and Technology. He's affiliated with the Chemical Engineering Department from Kalashakaoku campus. He's currently working as assistant professor, and he has published more than 20 publications in the areas of membrane technology and polymer composites. So over to you, Doctor. Please kindly share your screen and start your presentation. Thank you.
Can you hear me?
Yes, Dr. Asif, we can hear you. Kindly continue.
Yeah, okay, thank you very much. And the topic I'm presenting here today is blend membranes comprising of polyethylamide and polyvinyl acetate for CO2 CH4 separation. And these are the contents I will go through today in my presentation. And if we look at the global energy source, natural gas shares 30% of it. So because it's considered as cleaner energy source compared to fossil fuels, and the impurity it got is CO2, which is highly undesired because it reduces the calorific value of natural gas. And in addition, in the presence of water, it can corrode the pipeline. So CO2 separation is very important for natural gas. And if we look at the conventional energy sources, we have absorption, cryogenic distillation, membrane separation for CO2 separation techniques. And membrane technology is getting lots of importance these days because its capital cost is very low and its operational cost is low as well. Its design is very compact and it's very easy to scale up. And if we look at the basics of the membrane, membrane is just a thin film which is used to separate, which is used as a separating barrier for miscible mixtures. And for example, the molecules which pass through the membrane is called permeate, and those which cannot pass through the membranes is called retentate. And the separation characteristics we define in terms of permeability and selectivity. So what is permeability? It's the ability of molecule to pass through the membrane, and selectivity is the ability of membrane to separate two molecules. Since we are talking about CO2 and CH4 today, so in the next sections, we will discuss about permeability and selectivity. So that's why I discuss here. And since we are working on blend membranes, for any blends, we use two polymers, for example, polymer A and polymer B. It could form either miscible blends, partially miscible and immiscible. And immiscible is highly undesired. So we choose two classes of polymers. One is glassy polymer, which offers higher selectivity because it has a higher chain packing. And whereas the other group is rubbery polymers, which offer higher gas permeation due to very loose chain packing. So basically in membranes, we desire not only selectivity and not only the permeability. So we want our membranes to perform in between, because if the permeability selectivity is high, which looks good actually, but the membrane is very slow. So we need the membrane with higher permeability and higher selectivity. So for that, specifically, we choose polyethyramide, and the rubbery polymer is polyvinyl acetate. And if we see at the graph here, which is Robson upper bond curve, so this is what is desired. So we want our polymers to reach as close as possible to this curve. And if we look at the polyethyramide, it has very higher selectivity. On y-axis, we have CO2CH4 selectivity. And the polyvinyl acetate, it has very lower selectivity, but the permeability is higher compared to polyethyramide. So that's why we choose these two polymers. And if we'll see, the research objective is, first of all, we want to optimize the solvent that we used, and then the physiochemical properties, so that we can optimize the blend ratio of PVAC into polyethyramide. And then since we are using it for CO2CH4 applications, so this performance is very important. So if we look at the methodology part, we use polyethyramide. We simply dissolve it in NMP at almost 70 degrees Celsius, and then we later on we add polyvinyl acetate, so that we can form a DOP solution. And for membrane synthesis process, we use phase inversion method, so that we can produce asymmetric membranes, and we use flat sheet membranes. We casted the membrane, and then we put in the solvent. Solvent we use is water, and then we simply dry the membranes. And once the membranes are ready, and then we can go through these characterization techniques, so that we can see the structure and the performance of our membrane. First of all, FTIR analysis. And if we look at the blue line here, which is pure polyethyramide, it's the curve is we can see, but when we add polyvinyl acetate, the curve is different. Especially we have two different peaks at 2930 and 3416, which shows that there is a CH bond stretching at this point. So it means there is some kind of bond formation between two polymers. And the thermal properties are very important, especially when we adding rubbery polymers. So as expected, there is no wet loss below 300 degrees Celsius, but after from 330 to 360, we have some degradation, and we have a permanent decline at approximately 440 degrees Celsius. So one thing is very clear. For example, if we see at the black line, which it shows pure polyethyramide membranes, so its thermal properties are higher compared to when we add polyvinyl acetate. So the more you add polyvinyl acetate, the more thermal properties you have to compromise. And the other thing is DSC analysis, which is very important, especially when you are dealing with the blend polymers. Since we want our polymers to, we want to know whether it's miscible or not miscible. So for example, first of all, if we see the glass transition temperature for polyethyramide is 212 degrees Celsius, and it gradually decreases as you increase the concentration of polyvinyl. For example, we have a single glass transition temperature here, which shows that our polymers are compatible.
Dr. Asif, we cannot hear you at the moment. Can you please readjust your mic?
Can you hear me?
Yes, it's
okay.
clear now.
Yeah, okay. And for the morphological properties of our membrane, we go through some analysis, and you can see since we are using dry wet phase inversion, so porous structure is expected. And we have asymmetric membranes. We have a dense layer at the top, and then we have finger-like pores. Since we are using NMP as a solvent, so which is very its demixing is very high with water, and these structures were expected. And but fortunately, we have no cracks or defect in the system. And the finger-like pores, it increases the permeability of the developed membranes. And this will reflect in gas permeation analysis. And if we see at CO2 permeance, if we see first graph, the pure polyethylamide, which is reflected in bold line black color, we run our membranes on 3 pressures, 2 bar, 4 bar, and 6 bar pressures. Those CO, and on x-axis we have CO2 permeance. So we see CO2 permeance is decreasing with increasing the pressure, which is again expected because the pores are filled with CO2 molecules, and when you increase the pressure, the permeability goes down. And if we see on the other hand side, CH4 permeance for the same pure polymer membranes, the trend is same, like you increase the pressure, the permeability goes down. But the permeance of CH4 is very low compared to CO2. And this is because of the 2 factors. Number one, polyethylamide, which is very have higher affinity for CO2 because CO2 is a polar molecule. So condensability and solubility of CO2 at polyethylamide surface is very high. And the other factor is the diffusion factor. For example, CO2 kinematic diameter is very low. It's around 3.3 compared to CH4, which has 3.8. So because of lower size of CO2 molecules, it can penetrate and pass through the membranes quickly compared to CH4 membrane. So that's why CO2 permeance is higher compared to CH4. And the other important thing to notice here is as you increase the polyvinyl acetate concentration, the permeance goes on increasing. And this is because, as we discussed earlier, because polyvinyl acetate has a rubbery structure and very loose packing, so it let the gas molecules pass through very quickly. And the other characteristic we want is the selectivity. We want CO2 CH4 selectivity. We want it to be higher, and that's why here, if we see when we increase the concentration of polyvinyl acetate, the selectivity keep on increasing at certain level. After 2 weight%, it goes down. The effect is negative because since after 3-4 weight%, the concentration of polyvinyl acetate is higher, which is rubbery in nature. So that's why the performance goes down. So the maximum value
Sorry
of
to interrupt, Dr. Asif, but we are above time. Can you please wind up?
yeah, this is very last slide. So maximum the selectivity we achieved is 30.33 for 2 bar pressure at 2 weight%. So our optimal membrane is containing 2 weight% of polyvinyl acetate. And if I quickly go through the conclusion, we successfully get miscibility of our 2 blends of our 2 polymers. And then thermal stability, we see we got single TG and thermal stability goes down, but not very high compared to the pure polyethylamide. And CO2 permeance is higher at 2 weight%, which is 40% increase, and optimal selectivity we achieved at 2 weight% at 2 bar pressure, which is roughly 26% higher than polyethylamide. So this is all from me. If you have any question.
Yes, thank you very much, Dr. Asif, for your presentation and sharing your insights with us. We have 2 questions. One from Zainul Abedin. He says, I am Zainul Abedin, DGM Product Development and Design. Please let us know how via DSC analysis polymer type PET or PA is identified.
How can you repeat the question?
Okay, he's asking that with the help of DSC analysis, how can we identify types of polymer like PET or PA? How can we identify them?
No, from DSC analysis, we are not identifying. We want to know what is the glass transition temperature, because it reflects the stiffness of the polymer. Since we are adding rubbery polymer into glassy phase, so we want to know how much we are compromising on the stiffness of the polymer. And this is the direct information. The other indirect information is if we have more than one glass transition temperature, since we are blending 2 phases. So if, for example, if we have 2 glass transition temperature here, it means we are in immiscible region. We don't have proper miscibility of our 2 polymers. So this is what qualitatively we analyze through this analysis.
Okay, thank you very much. We have another question from Dr. Asif. He's asking, gas separation membranes undergo plasticization. What measures we can take to control this problem?
Oh yeah, if we see here, we go up to 2, 4, and 6 bar pressure. We, for example, I know because I worked on polythermide already. Polythermide go for plasticization when we are high, when we go at higher pressure, for example, 8 bar or 10 bar pressure. So that's why we, at the moment, this is not the scope that we are dealing with. So we want to work in the safe limits. That's why we are working with 2, 4, and 6 bar pressure.
Okay, thank you very much. Thank you, Dr. Asif, for your presentation.
Thank you very much.
Thank you. Our next speaker for this presentation is Khazar Hayat. He's from University of Management and Technology, Lahore, Pakistan, and he will be presenting on machine learning based prediction of elastic properties of woven fabric reinforced plastic composites. He is affiliated with Mechanical Engineering Department, School of Engineering, University of Management and Technology, Lahore. He's a professor and have 17 international journal articles, and his areas of expertise are design and manufacturing of composite structures, finite element methods, structural health monitoring. Thank you, Dr. Khazar Hayat, for joining us. You may start your presentation now.
Thank you, Mr. Speaker. Can you hear me?
Yes, we can.
Okay. So I'm Khazar Hayat and I hold PhD in mechanical engineering. Currently, I'm serving at University of Management and Technology. And the topic of presentation is machine learning based prediction of elastic properties of woven fabric reinforced plastics composites. And my fellow colleagues who participated in this work are Dr. Shafaq Siddiq and Amir Shahzad from Mechanical Engineering Department, the University of Lahore. Before I begin my talk, I would like to share the table of contents that includes motivation and the theoretical background that involves multi-scale analysis and different kind of weave architectures in case of woven fabric composites. And then it will be followed by methodology, and that is consisting of two-step homogenization and comparison of finite element methods versus machine learning based approaches. Finally, I will present some results, and then there will be final remarks. Regarding motivation related to this topic is woven fabric are increasingly becoming popular in various structural applications. For example, automobiles, aircraft structures, as well as marine applications. And there are several reasons, but most importantly, they have higher out-of-plane stiffness, strength, and toughness. They are more delamination resistant and damage tolerant. They exhibit better drapability, and they're easier to handle if we compare all these parameters with respect to unidirectional composite materials. So woven fabric are much more convenient. They can reduce the production time. Whenever we have to perform design and analysis related to composite materials, especially woven fabric composites, we need elastic properties. Experiment is one way through which we can estimate the elastic properties, but they are expensive. Most of the time we perform finite element method-based simulations, which are complex and time consuming. So end user always feel a kind of burdensome whenever they try to design a structure made of composite materials. But with the help of machine learning techniques, we can train a certain models, and these models can be finally used by end users with the minimum involvement. So that will be very productive in terms of time. But for this machine learning algorithms and their training, we need data sets, and that data sets either are coming from experimental side or from finite element methods. So computational cost is not avoidable, but we can train our model using the data set generated from experiments and through simulations. And once that model is trained, then user can simply plug in their inputs and evaluate the elastic properties of woven fabric composite with least time. So this is the idea. So here I would like to explain the multi-scale analysis, which is almost unavoidable in case of design and analysis of composite materials. It can be explained in terms of a pyramid. At the top of pyramid, there is a structure, and composite structure is made of different kind of laminates, and each laminate comprises several plies. In our case, the plies will be woven plies, and computationally, these woven plies can be represented with repeated meso-unit cells, and each yarn or tow in woven meso-unit cell can be represented with a micro-unit cell that consists of fiber, matrix, and interface. So theoretically, we can say these fiber, matrix, and interface covers all kind of composite structures. So these are the basic building blocks. If we know the fiber, matrix, and their interface properties, then we can estimate the properties of this meso-unit cell representing the woven plies with the help of woven geometrical parameters. And once the ply elastic properties are known, we can estimate the laminate response with the help of classical laminate theory or some other methods. And finally, we can estimate the stiffness response of a structure. So homogenization and localization are two key concepts that are related to multi-scale analysis. If we are doing scaling from higher scale to lower scale, we call it localization. On the other hand, if we are going from bottom to upside of the pyramid, we call it homogenization. So these are key concepts that are related to multi-scale analysis of composite materials. Talking of woven fabric composites, typically there are three types of woven fabric available: plain weave, 12, and satin. And those woven fabric geometrical patterns can be estimated in terms of these geometrical parameters, like toes width can be defined with this parameter width, and we can also describe its thickness using the symbol T. The undulation can be described with the amplitude and a wavelength parameter, and the gap between different toes can be adjusted with this toe adjustment gap parameter G, and different kind of V pattern can be controlled using these symbols N and M. So if we manipulate these parameters, then we can generate various kind of weave patterns. So here are some examples. So talking about the methodology, how we typically evaluate the elastic properties of woven fabric. So we is shown here. So there are 4 elastic properties typically we needed for design of a composite structure: in-plane stiffnesses and in-plane Poisson ratio. So to estimate these in-plane stiffness properties, we do 2-step homogenization. In the first step, we do homogenization at the macro unit cell. We have fiber and matrix properties. From these properties, we estimate the properties of toe or yarn of a woven fabric composites. And then we add geometrical parameters in the meso-unit cell, and finally we estimate the in-plane elastic properties of woven fabric. So conventionally, these input features we plug it into finite element based 2-step homogenization method, and at the output we get these 4 properties. So in statistical terms, the input parameters are also called input features, and the outputs are named as responses. So this is the conventional approach, which we are saying that is time consuming and computationally expensive, and we need a lot of skill to perform this kind of finite element analysis. But with the help of machine learning techniques, which is shown here, we should have a data set. So again, this data set can be derived through simulations or through experiment, and then we will apply some machine learning technique to train a model. So finally, once this model is trained, then we can share this model to the end user, and end user have to simply plug in values and get the outputs with almost no time. So we are actually reducing the computational burden for the end user who is designing a structure made of woven fabric composite. So in our case, we generated data set through finite element methods. For that purpose, we have to validate our finite element model. So these are the properties shown here we used for a validation of our finite element model. We also performed mesh density study, and we applied periodic boundary conditions.
Dr. We are a bit behind the schedule. Kindly complete it.
Okay, so we got a reasonable agreement when we compared the experiment versus the simulation result. So that means our finite element model is giving a reasonable accuracy results. So once we generated the data set through finite element simulation, the size of data set is approximately 375. And the number of input features are 13, and output features, which we wanna estimate, are 4 elastic properties of woven fabric. And at the figure shown below, there is a representation of statistical variation of various input features. In machine learning field, there are several methods to train the model. For example, the MATLAB regression app provides these 6 methods. We used the first 5. Neural networks were available, but we haven't used them. And we measured the accuracy or assessment of the model in terms of root mean square error. And we found out that the Gaussian process regression model is the most effective in our problem. So we used Gaussian process regression model, and these are the result which are showing in terms of scatter plot. The relationship between the true values and the predicted values, and as you can see that all data set is very close to the diagonal line. That means there is a very good correlation, and our model predictions are quite accurate. So in terms of numbers, you can see that except in-plane shear stiffness, for other in stiffness values, we have a reasonable agreement. And in terms of computational cost, if we compare the results, and you can see that if we perform finite element simulation, which is the conventional approach, it takes almost 10 minutes to estimate these 4 elastic properties. But once we have a trained model through machine learning techniques, it takes less than 2 minutes. So the processing time is almost 700 times faster. We also performed principal component analysis, which is a technique through which we can convert a high dimensional problem into low dimensional problem. So we were able to reduce 13 features to 8 features, but on the cost of some accuracy, but still excluding in-plane shear modulus. For other in-plane mechanical properties, we have a reasonable agreement. So this is the last slide of my presentation. We were able to use machine learning techniques to significantly reduce the design or analysis time for the end users with the help of machine learning based trained models. And we also were able to reduce the input features with the help of principal component analysis technique. And we also found that in our problem, which we try to solve, the Gaussian process regression model is comparatively better in performance as compared to other machine learning techniques. Since in this work, we used a data set that was generated from finite element method. If we add experimental data, then of course we can increase the reliability of the trained model. And in this work, we focused on only plane weave fabric composites. But of course, this method can be extended to other types of woven fabric like twill and satin. And also it would be interesting if we able to apply the neural networks and compare its performance with the Gaussian process regression model. So that's all from my side.
Thank you, Dr. Khizer. It is indeed a very interesting technology, machine learning. So I have just one question. Can you please elaborate about the percentage of prediction percentage of this Gaussian process regression comparative to other techniques? Can you please elaborate on that?
We do not have that slide here, but we have some backup data through which we selected that Gaussian method is more appropriate as compared to other machine learning techniques. So if you're interested, I can share you later on. I mean, through email or whatever you like. Right now, I do not have that slide.
Okay, we have another question. Do you think that the data was enough to make a conclusion on the machine learning approach as you had 13 input attributes?
No, I think we need more data. Especially this all data is coming from finite element methods. Especially we need to include experimental data. But of course, the higher the value of data sets we have, the more accuracy we can achieve through these techniques. So currently, I would say it is not that accurate, but still, I think it is workable. At least we know that how much like time we can reduce. So of course, the more data we have, we can better predict the elastic properties of woven fabric. So in a nutshell, data is insufficient, but of course we need more data. But again, training takes some time and some computational cost, and we are working on that.
Okay, thank you, Dr. Khizer. We are thankful for your presentation. Our next presenter is Ms. Adila Mukhtar from GC University Faisalabad. Her area of interest is polymer zeolites, and she will be presenting on sonication assisted synthesis of flashboard zeolites for wastewater treatment. Okay, over to Ms. Adila. Yes, Ms. Adila, we cannot hear you. Please turn on your mic.
Assalamu alaikum, sir.
Yes, we can hear you. Please continue your presentation. Please share the slides.
Assalamu alaikum, sir. I am Adila Mukhtar. I am from Government College University, Faisalabad. My topic of presentation is synthesis of fly ash-based zeolites for wastewater treatment.
Miss, we are a bit behind schedule, so please complete in less than 10 minutes, please.
Okay, sir. Okay. Introduction. In today's world, water is a major abundant natural source of ecosystem. And in today's, due to urbanization and industrializations, are causing serious pollutions, causing water pollutions. Industrial effluents contain heavy metals, dyes, and other hazardous pollutants like dyes, waste, heavy metals, and oils, and other organic and inorganic toxicants. So heavy metals such as zinc, lead, chromium are the major source of water pollutions. Water pollution are causing diseases in human like cancer, respiratory disease. So there is a conventional method to synthesize zeolites. Some methods are biological methods. They have also some drawbacks. Biological methods are ineffective and time consumption methods, and chemical coagulation is also time consumption, but it produces toxic byproduct and other high capital and operational cost. So are the heterogeneous materials containing silicon oxide, aluminum oxide, iron oxide, calcium oxide. So it has major constituents to synthesize zeolites. Zeolites are aluminosilicates with exchangeable cations. They are thermally and chemically stable. They have micropores and their pore size varies from 3 to 12 angstrom. So metal purging using synthetic zeolites are used for wastewater treatment. Fly ash-based zeolites are negatively charged surface have negatively charged surfaces, which is used as solvents to remove positively charged contaminants from wastewater like toxic metals. Zeolites possesses excellent ion exchange properties with metals. So the absorption ratio of zeolites toward metal cations match the linear and friendly isotherms. Why there's a need for this project is due to the compositional versatility of zeolites and application in wastewater treatment. It is very logical and reasonable approach to develop some zeolite material for wastewater treatment. The increase in surface area and synergetic impact of zeolite is expected to work as energy efficient material for wastewater treatment. So aims and objective of this project is to synthesize coal fly ash based zeolites using alkaline techniques. We will characterize this draw fly ash using different techniques like XRT, FTIR, and SM and ICPOES. What is the material and methodology to synthesize zeolites from coal fly ash? First of all, we'll do sampling of coal fly ash, then synthesize zeolites from coal fly ash through sonicated assisted synthesis technique and some conventional technique, hydrothermal technique. By this, we'll synthesize fly ash based zeolites. We'll characterize it by using FTIR, SEM, and ICPOES. And then after characterizing, we'll do its applications in wastewater treatment. Then do statistical analysis. Materials and methods. The second point is sampling and pre-treatment. First of all, we'll do sampling of coal fly ash, which is a raw aluminosilicate source from electrostatic precipitator of the boiler plants in different industries of Faisalabad. In this, we will do a sonication-assisted hydrothermal technique. We will take 50 grams of coal fly ash and 50 grams of sodium hydroxide and grind it and make a hydrogel formation. This hydrogel is treated with sonication treatment. In this, then we will provide hydrothermal technique. In this, we will provide 100 degrees Celsius temperature at different time. Then we filtrate and synthesize the zeolites and we will dry it in oven. I have discussed earlier a characterization of zeolites by FTIR, SM, XRD, ICP, and OES. By FTIR, we will find surface chemistry functionality. By using SEM, we will find surface morphology, particle size. By XRD, we will find crystallinity and mineralogical compositions. And ICP-OES, by using ICP-OES technique, we will find leachability of metals. So statistical analysis data will be presented as mean plus minus standard deviations, and all the analytical experiment will be performed in 3 replicates. And then we'll provide references. Thank you so much.
Thank you, Ms. Adila, for your presentation. So this session is already behind schedule, so we are not taking any question so far. So with this, first session of our second day of second international conference of polymer and composite is finishing. So we are. I now request Dr. There will be a 5-minute break, and for the latter session, it will be chaired by Dr. Zaderihan and his co-host. Thank you.